Okay, welcome to AGEC 305 Lab 1, where we're going to be estimating demand in Microsoft Excel. The purpose of this is just to get us started, just some quick practice, demonstrate the steps that you would go through to estimate a demand curve or a linear demand relationship. It's going to be simple and straightforward, and so hopefully you can follow along without any trouble. To get us started, there are a couple of files on the class website. The first of these is the actual data file here, the AGEC 305 or AGEC 305.lab.1 Excel file. So you can you can download that, and we'll all have the same data file, the same starting point, and we'll look at that in just a second. And then second, we'll have the on the class website is the lab handout. So that is a long document that you can use. I know some people don't like to have a video playing and try to pause it and keep up with the steps, so hopefully the lab handout would let you do that as well. Everybody should listen and follow through this lab presentation, but it's not necessary that if you think you could learn it better by using the handout as a guide and going through the steps, then you could potentially do that as well as an alternative, rather than having to keep backing up the video and trying to replicate the steps. So both things are there, and use them to learn how you learn best. The first thing we're going to do is plot the data. Okay, so we need to open up our spreadsheet, look at the data that's been provided, and we're going to do a plot and look at some other things that go along with that. So let me bring up my version of the spreadsheet, and you'll see here that there are 6 observations. So it's a small data set. It's actually the data set in the example from Gujarati, Chapter 1, the reading that we've been looking at. So you're already familiar with it. You can see it's a contrived data set. It's been set up to help us get a real look at data that would be designed to build out a demand curve, right? Because they've varied the price between 0 and 5 and then given us the associated quantity for each of those. Okay, real world data doesn't happen this way. You can't get everyone to charge every price and then tell us what quantity is there. Maybe if you did an experiment or something, a survey experiment, you could, but even then it wouldn't be real responses. But anyway, it's a good example to learn from, and so that's what we're going to do now. So our first step is we said to plot the data. I'm just going to highlight a cell over here to the side and hope that that helps me get started with the plot. So the kind of plot, or the kind of graphical tools in Excel are under this Insert tab here at the top, and they're called charts. Okay, so you see here all the variety of different charts they have. You can even highlight your data, and it'll tell you which charts may work best for you. But the one we're going to use is this one right here. It's called the XY, or the scatter plot. Okay, and it's important type of graph, because anytime you have X and Y data, or you think there's some causal or correlation relationship between two pieces of data, the scatter plot is the kind you want to use, because it doesn't use labels for either of the axes. It uses numerical values on both axes. So if you're trying to uncover some correlation or some causal relationship, that's what you want to use. I'm going to choose the dot version here, so you can see all the different pictures that you can, the kind of basic graphics that will show up when you plot your data. And for mine, I'm going to use this one that's only just points of data. So I'll click that. I'm going to move my graphic up here beside this. And you see that it's given me two series of points plotted, and that's not what I want. I want price on one axis and quantity on the other axis. And what it's done is it's assumed that I wanted observation number on this axis and then to plot both things against the observation number. And that's not interesting to me. That doesn't mean anything. The observation number is irrelevant. So I'm going to click Select Data. I'm going to ask it to remove both series of data. So what I'm left with now is this blank field here. So this is my graph space, and it's saying right now that there's no data entry. Okay, there's no data that's been selected as something that should be plotted. So we can fix that by clicking on Add. I want to give my series a name. I'm going to call it Demand. And then these little red arrow buttons here to the side let you fill in this field right here for the series of X values. By clicking on the red button, it opens this and it's ready to take in a selection of cells from the spreadsheet. Okay, so I've clicked it. It's saying edit the series. The thing I want on the x-axis here is price, so I'm going to highlight all of the data on price that I have. I'll click my red button again, and we see that it's filled in the series of X values. For a default, it puts 1 in for all the Y values, but that's not what I want. So I'm going to click the red button next to the series Y values. I get the Edit Series box again, and now I'm going to highlight all the quantities I have in my data. Pull that up, and we have everything filled in. Close out with OKs, and now we have what we intended. We have price on this axis, quantity on this axis, and that's the demand relationship that we wanted to look at. There's certainly a lot of things you can do at this point. The first thing I always do, so I remember what's going on here, is I will go to Design, which has been clicked, and then over here to the left on Add Chart Element, and then it says Axis Titles. So I'm going to name these things so that I get titles right under the X and the Y axis that will keep me mindful of what I'm actually putting together here, what this graphic is going to represent. So the primary horizontal, when you click it, it becomes available to edit, and you can type in price, and that shows up. And then I'll go back to Add Chart Element, Axis Title, Primary Vertical, and then I'm going to type quantity. Okay. So now I have a complete graph. It does. It has the notes that I want on each side. I might just click in there and make those a little bit bigger so that they're easier to read. Okay, so I'm changing the fonts on those. I might change the values here as well. You can click and edit the fonts. So I'll make those 16. Okay. And then yeah, so that looks fine. So we see our plotted points here going from the price of 0 down to 5, and you see it's sort of moving down. It's a little hard to tell, but we'll figure out more about that as we move on. Let's jump back over to my slideshow so I can check on the things I want to talk about. Yeah, so this is just a reminder here that the XY scatter is important because it treats the x-axis as numerical values. If you use something like a line graph, if you use a line graph, that doesn't happen. It just uses labels for that part of the graph. Okay, so the x-axis would just say like year 1, year 2, something like that, without trying to respect the fact that numerical data were being used. Okay, so one of the nice things about the sort of built-in graphing tool in Excel is it gives you this automatic option to add a trend line. So you may be familiar with what a trend line is. I'll do a quick example here. So if you had points of data that look something like this, and you wanted, you were asked to, what's the trend of that data, you might say, well, it looks something like that, some kind of line that goes through them, or you might say it looks something like that. And people look at data all the time. They try to mentally summarize the data. Is it going up? Is it going down over time? And it can be complicated sometimes. So this is a really nice built-in feature. Trend, the word trend, comes from time series analysis. Okay, so that's where you're usually looking at how something changes over time, something like interest rates or unemployment. What's the trend in unemployment? But we can use it for any kind of data where we think there's correlation between the two. And in fact, it's just what we call a built-in in Excel. So it's this automatic function that does linear regression for us. Okay. The nice thing about the trend line that we'll see here is that it has some built-in options as well. So at the same time that we're producing a trend line through our data, we can look at an equation that describes the trend line. And we look at the R-squared. Okay. And the R-squared, we'll see, is an important measure of how well our trend line or any regression model fits the actual data that we're looking at. So let's bring back up the Excel picture here. And so the thing I'm going to do to create this trend line is I'm going to close that little box there. I'm going to click on one of the data points, and you'll see that it's marked all the data points as active. So it's basically saying, okay, I'm looking at your data series on demand now. What would you like me to do? And so if you hold the cursor over one of those points and right click, you'll get some options here. Okay, so one would be to delete, not interesting. If you wanted to edit your data, you could select it and open back up the data entry fields for the graph and make some changes there. So that would be available. But what we're interested in is the add trend line. And so I'm going to click on add trend line, and you'll see the first thing it does is it adds this dashed line through my data. And then the second thing it does is over here it opens up the format trend line box. Okay, so these are all the options you have when you create a trend line. Alright, so first of all, we note that this is a downward sloping trend. That looks fine. And we can come over here, and there's a couple things I want to do. One is click on this box that says display the equation on the chart. And then the other thing I want to do is display the R-squared value on the chart. So you see it puts those in together as kind of a text box. Again, I don't like these things showing up so small, so I'll just click and increase the font. And what we have here is an equation. Y is equal to negative 3.8x plus 76. So right here we have the intercept of this equation, the estimated intercept of this trendline equation. And here we have the x variable. Whatever is on this axis is the x variable. And we have the slope. Okay, so the slope is negative 3.8. And so that tells us, we've confirmed that we are getting this downward sloping relationship between the two. The final thing it shows us is the R-squared equal to 0.95. The R-squared is a measure of how well does this dash line, the trend line, fit the points, the true points. So the points of data here are considered truth, or real world measurement. The trend line through here is considered a forecast or an estimate or an approximation. And so this R-squared says on a percentage basis, if you go point by point through here, how much error would you get if you ignored the real world information and just chose the point that existed on the trend line? And this is basically saying that 95% of the time, or you would be 95% accurate using just the trend line. Another way of putting it is, we have better definitions over here in the PowerPoint for this as we go through here. So So the equation of the trend line is able to be viewed there. The R squared is able to be viewed. And then here's the definition. So R squared is a percentage measure, and it's bounded. Okay, so R squared will show up between 0 and 1, and it's something that we call a measure of the explanatory power. So the closer you get to 1, the higher the explanatory power of the regression or the model or the estimation is. And then this is the way I like to define things as well. What question do we answer when we look at the R squared, or what question is that statistic answering? It's basically what percent of variation in the dependent variable, something that we saw in class the other day, a definition, the left-hand side variable, or in this case the quantity. What percent of the variation that we observe in the data on quantity could be explained by the variation in the independent variable, or in this case, the price. And you can see I put an S out here in parentheses because it's true that we could have a number of independent variables. Okay, so that's the power of the R squared. It's this important sort of first look check on how much correlation is there between our two things. Okay, theory tells us that price should cause demand response, and then statistics tell us how well does it work, how well does that theory fit with what's going on. The last thing we should think about here are the functional forms. That's basically just the shape. What kind of line or what kind of trend line are you trying to fit through your data? We chose linear, but we could have chosen logarithmic or polynomial. Both are relevant, and so we'll check those out back in our spreadsheet here. So if I click on the format trend line again, you can see over here it's actually giving me these little previews. What does a logarithmic trend line tend to look like? And so if we switch it, in this case, I'm not sure why it wouldn't let me. Oh, so since one of the observations is 0, you can't do a logarithmic trend line. So that makes sense. So let's add it back and go to polynomial. So something with some kind of bend. So a polynomial is like a quadratic equation is a polynomial. It has x and it has x squared. So in this case, you're probably getting something like, what is it if you had price plus price squared being equal to this? So it didn't change my equation, but it gives me this bent. Right? You see this small curvature that happens, and so you can see why that might be a little bit better fit. Okay, that's about the end of our path on trend lines. Now we want to go into more formal regression analysis. So trend lines as a built-in feature in Excel is great because you've got to plot your data first anyway. Even if you had a number of things that you were using to explain the quantity demanded, it's still appropriate to look at plots, x versus y plots of each variable, and look at the trend lines through those to get these sort of ballpark estimates. But when we're ready to do our analysis, we want to move over and do the full regression type analysis using the built-in there. Okay, so the first thing we have to do is make sure that you'll have to do this. It's already in mine, but underneath the data tab, there's a section or a menu called data analysis, and that is where you'll see things like histogram and ANOVA, some other things that you may have seen before. But regression is also one of the tools there. So bringing back the Excel sheet here, I'm going to move my trend line graph out of the way and show you where this is. So under the data tab here, move all the way to the right, under analysis, I have this data analysis menu. Okay, now if for some reason that didn't show up in your version of Excel, it's possible you won't see this analysis box at all. If that doesn't show up, then what you need to do is click on File and then scroll all the way down here, or roll all the way down to the bottom where it says Options, and this is the Excel Options. And then in the Excel Options menu here, you're going to click on Add-ins. Okay, and this brings up all the things that are possible to add on to Excel Sometimes these things aren't. So when Excel was installed in lots of times in computers, these add-ins to save space aren't automatically installed. No, they're available, and they can be added, without any downloads or anything. Um, so they're there. They're just compressed. They're not showing up because they haven't been added in. And so all we would need to do is go on add-ins. If you click on Analysis Tool Pack and then click OK, it should add those in. I'm not going to do it because it's already been added into mine. Okay, so once you get that to show up, then it's just a matter of clicking on the Data Analysis tab. These are all the options. So you see ANOVA, correlation. You can do some histogram, moving average. You can do your random numbers. Lots of things available, but we're just going to click on regression and then click OK. And that gives us the regression input space, or the input form. Okay, and so we see the familiar red boxes here telling us that we can go, if we click on that red box, we can enter a field or a set of cells, or a range of cells, I guess it's called, into our data here, and then proceed through the regression. So for the input Y range, I'm going to click on that, and the quantity, remember, is my Y variable. It's on the vertical axis. The X variable is going to be price. So I'll click again on the red, highlight all of the price observations. And now we have some other things here. So I'm going to click on output range and the red button there. And I'm going to pick that cell right there. And that means that when it writes the regression output, it's going to start from that cell, and it's going to write it right next to my data. I don't want it to open in a new worksheet or anything. Then we have some other options down here at the bottom. So residuals, standardized residuals. These are things related to the error. Okay, and we might want to plot those at some point, but for now I'm just going to click on the line fit plots, and that should look like my trend line analysis. So hopefully that graph will show up and say, this is the regression model's prediction of what the quantity should be for any price, and this is what your data showed as actual observation. There's some other things here. You could do labels. Constant is 0. Confidence interval, that's set automatically to 95%. That's a standard in econometrics, is to choose 95% for your confidence intervals. Click on OK, and you see the output shows up. Okay, so let me highlight these, make those a little bigger. Something like that. Expand those out. I'm going to go ahead and ditch my my trend line there. Yeah, and so we get all the output that we might be interested in. The first thing we do down here is I'm going to look at the coefficients. You see the X variable 1, that's the price, right? That's the only X variable we had. That coefficient is negative 3.88. That's the same thing the trend line showed us. But for now, let's step back out to the PowerPoint slides, and then we'll come back to the results after we get some more definitions and some more explanation of what's going on here. Yeah, so Excel's regression output, the printout that shows up when you hit OK on the regression, to go ahead and execute the regression or implement the regression, is separated into a couple of fields. So the first thing is sort of generic results, or what we call diagnostics. So how well does your statistical modeling, how well did it perform? And so the first thing that we might look at up there would be this this measure R squared. Okay, sorry, there it is. So the R squared, and so we've talked about that already. It's this goodness of fit measure, right? It's 0 is the lowest value it takes, 1 is the largest value it takes. It's not always the case that R squared can be looked at out of context. You can't just say, I want that thing to be really close to 1 because there's some data, some problems, some estimations where R-squareds like 0.3 or 0.4 are considered quite good. Something else we'll look at is called the f-test, and this is the R-squared is sort of this heuristic. It's a percentage measure. The f-test is a true test built up against a test distribution or a sampling distribution, and it looks at the R-squared or the information that's contained in an R-squared, and it says, how well did you do in this regression? How, can we test it and say that you have some significant relationship being modeled here or not? The f-test answers the question, does your regression model have any significant explanatory power overall? Right? Is there something about the way you've set this up that tends to explain the variation in the dependent variable? Okay. So here you say, is there enough correlation between the x or all the x's that you've chosen and y, right, the dependent variable, to justify this as a better explanation than looking at y by itself? Okay, so independently of x means just looking at the average of y. So if it doesn't have any explanatory power, the f-test would fail, right? It would show up as not a significant result. The second piece in the model output is the model results themselves, and so you would look at those and see things like your coefficients. Sorry, there it is. The coefficients or the parameters, and those are the estimates in this case of the intercept and the slope for our linear demand equation. The second thing you'll see are the standard errors. So every time you estimate a coefficient in a regression model, you have a point estimate or sort of the average effect, and then you have a standard error that goes with it. It tells you, how much error is built into that estimate. Okay, so low standard error is good. Being low relative to the coefficient is good. And the t-statistic actually formalizes that into its own distribution concept, because the t-test statistic is actually measured as the coefficient divided by the standard error. Okay, and so there's a basic distribution that's looked at. It's called the student t distribution, and you compare your coefficient divided by your standard error to the values in that distribution table, and it tells you if you have something significant or not. Now we don't have to do the table lookup anymore because it's built into Excel, but used to you had to flip to the back of your book and look through the t-table and see how well for any number of for the number of observations you have in your data, how well did your regression do. Okay, so it's a test on significance of individual coefficients. The reason we don't look those up anymore in t-tables is because this value, the p-value, is now calculated directly. Okay, so the p-value says, if you were to look this up in a t-table, what would be the 1 minus the confidence interval or the confidence level you would find for that t-statistic? So it's actually the case that a low p-value is good. So if you want to be 95% confident in something, then the p-value needs to be lower than 0.05, and that's the standard that we'll adopt and work with for a while. And then finally, the confidence interval is presented as part of the results. So the confidence interval you probably have the most experience with, and that just gives you the range of values, some value above and below your coefficient that you could say represents the range that you are 95% confident contains the true coefficient. Okay, so usually what we're looking for there is, if we have an estimate like ours of negative 3.8, does the confidence interval also include 0? Because if it also includes 0 and it goes over into positive numbers, then that's a problem for our theory here, because our demand theory says this needs to have a negative slope. The price-quantity relationship should be negatively related. And so that'll be something we'll be checking in our confidence intervals. Okay, so let's just go back to our spreadsheet for a final run through and look at all of our results. Okay, so we said the R-squared, so here you see it to quite a few digits. It's the same thing we got from the Trendline estimation. And then as you move down here, as you move down here, you see the F statistic. So F statistics, again, you'd have to go look it up in a table, but this right here is telling you how significant is your F statistic. Again, taking 1 minus this value tells you the confidence level you would have. So 1 minus this is essentially 99.9% confidence. So this is actually a high value regression. Anytime you have a very high R squared, you're going to end up with this being positive. The meaning of the F statistic, though, is that as long as you qualify here, right, as long as you have the significance level you want, then it's not a confirmation. It's just you fail to reject that your model has no power. Okay, so there's a kind of an interesting language around statistics and regression that we'll get some practice with. But for now, just note that if you meet the conditions here, then you move on and start analyzing the actual model results. So the sort of diagnostic stuff is up here, and then the specific stuff about your model is down here. So the first thing is the coefficients. You see these are again the same as we had in our trendline analysis. So we're saying our demand model from this data is Q is equal to 76 minus 3.88 times P times the price. So those are our coefficients. These are the standard errors that were estimated as part of the regression. So this standard error goes with the intercept 1.3, and this standard error 0.43 goes with this coefficient, the slope coefficient. These are small relative to the coefficients, and that's shown up here in the t statistic. So take the coefficient, divide by the standard error, and you get the t statistic. I think we can check that. It may be that you don't get exactly that. Yeah, but you do. Okay. So sometimes you'll see people divide, multiply by n and divide by n minus 1 to do a correction, but not in Excel, evidently. So these t-stats look pretty good. A general rule when you have normal data observations or normal size data sets, usually around 30, is that you want your t-stat to be 2 or larger. Okay, just as a rule of thumb. That's the way to summarize the t-table. Again, like we said, we don't have to do that because we're getting the p-values that come from the t-table here. So what we're looking for here, what we're looking for here are these to be less than 0.05. This is 5.272 times 10 to the negative 7th power. So that's a very small number. So when you see something that looks like this, it looks a little strange, always check the e value. That says this is going to be an exponent. So whatever this number is, it's multiplied by 10 to the negative 7th power. So that's a lot of zeros before you ever get to a number. And so it's 0.0 with 6 zeros, I suppose. And then here we see this is a very small number as well, so much below 0.05. So that's telling us that we have what we call valid test statistics. They would hold up against a hypothesis that the intercept is not equal to 0 and that this coefficient is not equal to 0. So that's what the basic t-statistic presented in the way we've given it here is testing. So because we might want to test it for something else, is our slope coefficient -1 or is it -2? That's why we go ahead and we just do confidence intervals over here. Okay, so the confidence interval gives you this quick look at what range would you safely say, right? Or could you say that 95% of the results, or sorry, 95, you have 95% confidence that the true value from the population data lies between two values. This is a very broad interpretation, a very broad distribution. And so in this case we would be saying that the coefficient -3.88, right, our estimate from this model is just one of many estimates. Okay, if you went out and you got repeated samples on this demand curve, you would get other values, but 95% of them would lie between -5.08 and -2.68. So from that you could go ahead and hypothesize, is the slope of this curve -2? And with 95% confidence, you would reject -2 as a hypothesized slope. By the same token, -6 also not within the confidence interval, so you could reject that hypothesis. Remember, when you do these things, or when you begin talking about these things, we're always trying to state a hypothesis and reject it, right? We can firmly reject things with certain levels of confidence. We can never, it becomes trickier to try to say that we've verified our hypothesis. So it's sort of the scientific method encroaching on our analysis. We will try to stick to that and remind ourselves of that quite a bit in this class. But then we'll also say, these are my estimates, the test statistics look okay, let's go ahead and work from this demand equation. Last thing I want to show, if I can find it here, is the line fit, the plot. Okay, so if we stretch this out and make it as big as the screen, and maybe change this axis so that it only goes from, let's say 50 up to 80. And let's take the predicted y's and we'll join those through with a line. And you can see what's going on in the regression model here. So these a little bigger maybe. Yeah, so anything in blue here is a true point, right? It's a point exactly from our data. And then the orange is what we call the predictive value. Okay, so the blue and the orange don't agree exactly, right? Ever, it looks like. So there's always some distance between the two. And this is where things like the R-squared come from, right? So it measures how much error is there, how much from the true value are we at the orange points, and it goes back and it calculates that error and it figures out what the average error is, and it says you're going to be about 95% of the 95% right. So sort of the average fit of this is 95%. The distance from any orange dot to the blue diamond, the difference between the fitted value or the predictive value and the blue value is what we call the error. And so when we wrote that model in lecture 4 on Tuesday, when we saw that model that was Q is equal to C plus D times P plus U, then we also said that you could take the predictive value, add U to it, the error, and you would always get back the actual observation. So U is are these distances, right? And remember that our least squares method is to square these distances so that they all end up, as positive and squared values, and you minimize those. And so that's how regression is working. It has a special formula for fitting this best fit line through here, and it allows it to calculate all of these test statistics or all these summary statistics like R-squared by remembering the information, remembering how far the blue dot is, the true value is from the predictive value. Alright, so that seems like a good place to close off. Hopefully you've been able to follow through and do some of this on your own. You have a few questions at the end of the lab handout to be handed in as homework 3, and I'll leave it to you, and good luck with this.